In this section, we're going to be looking at enthalpy. So enthalpy is sometimes called the heat content or the heat of reaction, and the values for absolute enthalpy of a system cannot be determined. So instead what we look at is we look at the change in enthalpy of a system. Enthalpy is a state property, so its value is determined by temperature, pressure, number of moles, composition of the system, but it's independent of the path taken. Typically when we're looking at enthalpy, we look at enthalpy or a change of enthalpy at SATP conditions. Okay, and SATP conditions are at 25 degrees Celsius, and this actually should say 100 kilopascals. That is SATP at 100 kilopascals. And remember, a change of enthalpy is a change of potential energy. It's a change in position, right? Potential energy is in fact positional energy. We've talked about before why chemical reactions are positional energy changes or potential energy changes. When a chemical reaction happens, atoms shift positions and they bond with new substances or other atoms. And so therefore they're changing their positions, and as a result we get a change in potential energy or a change in enthalpy. Combustion is a form of chemical reaction in which atoms rearrange and form combustion products. So we have an enthalpy of combustion. When things dissolve, they break apart from their crystal lattice and are surrounded by solvent molecules. And so therefore we have a change in position. So this is delta H of solution. Heat of neutralization is when you have an acid and a base reacting. Heat of formation we'll talk about in a second. And then heat of decomposition is also a form of chemical reaction that we're going to discuss later on in today's lesson. Now, enthalpy changes can be expressed either as a total enthalpy change, so the total number of kilojoules released or absorbed by a given quantity of substance reacting. So we calculate total enthalpy change by taking the moles of substance reacting and multiplying them by the molar enthalpy. So moles of substance reacting, so we take our moles of substance, how many moles we have, we multiply by the kilojoules released for every 1 mole, and as you can see, by taking moles and multiplying them by kilojoules per mole, we can find the total amount of kilojoules released. We can also use the molar enthalpy of change, and that's if we were just looking at the kilojoules for every 1 mole. So we can rewrite that as kilojoules for every 1 mole of substance reacting. As a refresher, we need to remember what our molecular elements are, and I'll explain why we need to remember them in a second, but our molecular elements are P4, S8, and then 8 Hofbrinkel, H2, O2, F2, Br2, I2, N2, and Cl2. Okay? These elements in their natural state are either diatomic, so they're bonded to themselves, or they're polyatomic, so bonded to several atoms of the same substance. So standard reactions, some of the standard reactions we have are standard heats of formation. And so I'll write the definition of what a formation reaction is right here. It's the heat released or absorbed when 1 mole of compound is formed from the elements at standard conditions. Well, you might be thinking, a reaction in which a compound is formed from the elements sounds an awful lot like synthesis reactions, and in fact, that's what a formation reaction is. It's a synthesis reaction where a compound is made from its elements. Now, as a reference standard, any element in its natural state under standard conditions has been given a value of 0 kilojoules. Okay. So again, because we're dealing with potential energy, we need to have a reference point. And so our reference point is any element in its natural state under standard conditions. The formation of that element is 0 kilojoules. And then we look at the change of position from that natural state. So the heat of formation for sodium as a solid is 0 kilojoules. Now oxygen in its natural state we discussed is O2, and so its heat of formation is 0 kilojoules. Like, that's our reference point. When we have a formation reaction, we have a heat of formation, and that's the amount of heat released for every 1 mole of compound formed. So it says, show the reaction specified. So a formation reaction of barium sulfate would look as follows. We have solid barium reacting with, and take some space so you can put in the coefficients after, reacting with sulfur, reacting with oxygen gas to form barium sulfate solid. Now, because this is a formation reaction of barium sulfate, I generally want to say for every 1 mole of barium sulfate. Now, typically we don't write the 1, so we'll leave that out. But I want this in terms of 1 mole of barium sulfate. Well, if I want this in terms of 1 mole of barium sulfate, my stoichiometric coefficient for oxygen has to be 2. My stoichiometric coefficient for barium has to be 1. But my stoichiometric coefficient for sulfur has to be 1 over 8 because I only need 1 sulfur. So in these thermodynamic equations, it's okay to use rational or fractional stoichiometric coefficients because we define things in terms of 1 mole of that substance. And so what we're saying here is we're saying that for every 1 mole of barium sulfate that forms from its elements, this is how much heat is released. Now, the more negative the delta H is, the lower the potential energy of the compound and the more thermally stable the compound is. Now, moving on from formation, we also have the standard heat of decomposition. And you might recall decomposition is just the opposite of synthesis, or in this case, since we're using the word formation for synthesis, we'll say the opposite of the formation reaction. Okay, I notice right here there's a 2, there shouldn't be a 2 there, so I'm just going to delete that. Okay, so let's write a decomposition reaction for PCl5. PCl5 would look like this. We'd have PCl5 as a solid, and it's going to break up into phosphorus and chlorine gas. We can see that the heat of decomposition is 398.9 kilojoules per mole. So for every 1 mole of PCl5 that is decomposed, this is how much heat is required to decompose 1 mole of this into its elements. Now I have to use stoichiometric coefficients. I've got to put a 1 over 4 here so I can just have 1 phosphorus. And since I need 5 chlorines, but this is 2 chlorines right here, I'm going to write over 2, so these 2's will cancel, and then I'll put 5 right there. So 5 over 2 chlorine molecules will give me 5 chlorine atoms. Okay, the last one is standard heat of combustion right here. And that's the heat released when 1 mole of substance reacts completely with oxygen to produce combustion products at standard conditions. All right, so let's show the reaction of butane, and I'll write C4H10 gaseous is going to react with oxygen. Again, I'm going to leave some room for my stoichiometric coefficients. I'm going to say it's forming CO2 gas, and because this is at, you can see that little circle there, 25 degrees Celsius and 100 kilopascals. That's going to be liquid water because at those conditions, water is a liquid. Now I just have to fill in my stoichiometric coefficients. I've got a 4 here and a 5 here. So 4 times 2 is 8 oxygens plus 5 oxygens gives me 13 oxygens. Well, I need 13 oxygens, so I need to get rid of this 2 there because I have an odd number of oxygens that I need, and I write 13 over 2. Okay? And the heat release, so for every 1 mole of butane that is burned under ideal conditions, I get 2,878.8 kilojoules of energy released. As we can see by the negative, that's how much energy is released. So those are 3 standard heats that we see very often. We see heat of formations, heat of decompositions, and heat of combustions. There are 4 methods of representing these enthalpy changes. And the first one is a thermochemical equation. And typically for thermochemical equations, we often have whole number coefficients, just for these types, for thermochemical equations, whole number coefficients. And we also have energy as a reactant or product. All right, so what do I mean by this? Well, let's write 1 mole of methane burning. Okay, so I've got my methane gas here. It reacts with 2 moles of oxygen gas to form 1 mole of CO2 gas and 2 moles of liquid water. And because it's an exothermic reaction, I'm going to put its energy as a product right here. Because it is exothermic, that is energy that is coming off the reaction, so 890 kilojoules. Now that's a thermochemical equation. We can also just do a regular chemical equation that doesn't necessarily have to have whole number coefficients. We can just write CH4 gaseous plus 2O2 gaseous goes to form CO2 gaseous plus 2H2O liquid, and then I just write the delta H after. Negative 890 kilojoules per mole. I got to make sure that it's negative here because I have to show that it's energy being released. Here it's positive, but that's because it's a positive product, which means that energy is coming off of the reaction. But if I want to show that energy is being released, I need to make it as a negative in using this notation. The other way is actually literally just writing this. Delta H of combustion of CH4, and then I just write the value, negative 890 kilojoules, and you can write it like this, kilojoules times moles to the negative 1, that just means kilojoules per mole. And if we see something like this whole equation is implied by this statement right here. The last way is with an enthalpy or potential energy diagram. And since this is an exothermic reaction, my reactants are going to start high, then it's going to drop, and then I'm going to have my products. So it goes CH4 gaseous plus 2O2 gaseous goes to form CO2 gaseous plus 2H2O liquid. Okay, and then I show that my delta H for this reaction is equal to negative 890 kilojoules right there. Okay, thanks for watching.